C'est comme honneur que je vous présente le professeur Alain. It's a great honor for me to present to you Professor Alain Aspect from the Institut d'Optique. Aspect is Augustine Fresnel Chair of the École Polytechnique. Many of you know Professor Aspect is a true pioneer in our field, having done some of the seminal experiments in establishing some of the foundations of quantum mechanics in experiments that go back now many years, in establishing the first real tests, serious tests of Kelvin qualities, to the development of single photon sources, to the development of laser cooling and trapping techniques that then evolved into being able to make Bose-Einstein condensates and study cold atom physics. We all owe, especially myself, a debt to Alain for all that he's taught us over the years and inspired us. Professor Aspect has numerous citations, some of them here. He is the recipient of the CNRS Gold Medal, the Wolf Prize in Physics, the Balazan Prize in Quantum Information Processing, and he's a member of scientific academies all over the world, including in France and here in the or a member of the national academies here in the U.S. And it's a real delight to have him here. Friend, welcome.
Well, it's a great pleasure to be here, in this place where there is so good quantum optics. Quantum optics for a long time, right? So today it will be about...
Is it too much you want to do?
I don't know. For me, it's no problem.
What do you prefer?
Ask them.
All right. I heard you all feel louder.
So my talk will, in fact, start from the fact that nowadays everybody is talking about quantum information, but how did it emerge? A few years ago, I typed quantum information in one of these strange search system, and it gives you 55 million results when you type quantum information. So I went through them and, and found some interesting results. For instance, you have a journal of quantum information. Est-ce que le micro est branché? Is the microphone on?
Yeah, it's probably not close enough is the problem.
You did it yourself.
I know. But as you love to point out, I'm not a theorist. So. Let's try again.
Careful with the Does it work? Is it better?
Turn up the volume instead of...
Test. That's my... Test.
Thank you. Now it's better. So you know, among the 55 million of answer, you find the Virtual Journal of Quantum Information, New York Times. Okay, this is the most famous physics journal. There is an Institute for Quantum Information in Caltech, in MIT, in Cambridge, UK. So you know, clearly it's something important, and even better. I was taking a taxi a few weeks ago, and the driver was taking me to the place where I had to give a conference. It was in France, in the south of France, in Nice. And the guy said, "What are you going to do?" I said, "I'm going to give a conference. A conference about what? About physics." And then the driver told me, you know, I like to invest in the stock market, and I have seen that there is this quantum computer business. Do you think I should invest in quantum computer? It's a true story. So, you know, it's really very important. And how did it emerge? Well, as I will explain you, it started with this famous paper by Einstein, Podolsky, and Rosen in 1935, and Bohr immediately replied. Schrödinger added his grain of salt, and we had to wait for another 30 years until Bell really made a very important contribution, and the conclusion is that entanglement is different. Different of what? You know, everybody, including Feynman, for many, many years say quantum mechanics is not like classical physics because of wave-particle duality, because of this possibility to add several trajectories. But after all that, people realize that there is something more, including Feynman. In his famous paper of 82, Feynman recognizes that there is something new, which is entanglement. So entanglement is different. But when Feynman recognized that entanglement is different, Feynman, being Feynman, not only found that it is different, but probably you can do something with it. The battery is dying, no? You have the feeling that the battery is dying. So Feynman concluded that not only it's different, but it is more. You can do something with entanglement, and what can you do is this, what we call nowadays quantum information. So let us see how it started with the 1935 debate between Bohr and Einstein, and the follower is there. You all know that Einstein made a founding contribution to quantum optics since in 1905 he introduced the idea of light quantum, and by the way he got the Nobel Prize for this, not for relativity. And if you want to know more about the fantastic contribution, in contrast to some legends, there is a legend that Einstein did not really understand quantum mechanics. It's not true. Einstein made fantastic contribution to quantum mechanics, and I highly recommend this book, Einstein and the Quantum, by a colleague, by a physicist, Douglas Stone, who is a professor in Yale. So we know, however, this is true, that after 1925, Einstein grew totally dissatisfied with the interpretation of quantum mechanics, which was given by what is called the Copenhagen School, that is to say, Niels Bohr and the people around Niels Bohr in Copenhagen. And Einstein tried to find inconsistencies in the formalism of quantum mechanics, and he first tried to find inconsistency in the Heisenberg uncertainty relation or dispersion relations, and he failed. It is well known. He was coming with objection. It was at the Solvay conference, for instance, in 1927, and Einstein would come with an objection saying, oh, the Heisenberg uncertainty relation do not apply to this situation, and then Bohr would come next morning and say, yes, it applies. Okay, so he failed. This is important. He failed when he was trying to finding inconsistency in the Heisenberg uncertainty relation applied to one particle. And in 1935, he found something which is relative to pairs of particles, two particles. And then he came with reasoning that I'm going to explain. And with this reasoning, he thought that he had found that the formalism of quantum mechanics must be complete. Bohr was totally unhappy with this conclusion, and in my opinion, and the opinion of many physicists, this time the reply of Bohr was not so convincing. Some people are convinced, others are not convinced. It's not crystal clear. And then we had, 30 years later, the input of Bohr. So what was the question which was addressed by Einstein and his colleagues? At the end of the story, Einstein was really obsessed
by the fact that quantum mechanics is only doing probabilistic prediction. Not that he did not like statistical physics, he liked, obviously, statistical physics. But he thought that the fundamental theory should not be statistical. For instance, if we describe the distribution of the velocity of molecules in this room, we are going to use a Maxwell-Boltzmann distribution. Fine, it's convenient. But we have no doubt that, in fact, there are many molecules. Each molecule has its own velocity, collision, etc., trajectory. So the statistical description is convenient, it's not the fundamental theory. And so Einstein had the feeling that quantum mechanics, giving only a statistical prediction, was not the ultimate theory. And in 1935, he thought that he had found a demonstration that indeed quantum mechanics is not an ultimate theory and that you must complete it by an underlying level. And I'm going to explain all that now. So I describe not the experiment, the Gedanken experiment described by Einstein and his colleagues. I take this one, but the ideas are basically the same, and I take this one because experiments have been done with a scheme like that. So we have two particles. Here, two photons, nu1 and nu2. They are different wavelengths, so there is no question on undistinguishability in this problem. So one photon is going to the left, one photon is going to the right. And we are going to make measurement of polarization. I suppose that many of you what is a measurement of polarization, but there may be some particle physicists who do not know. If they do not know, just think of Stern-Gerlach measurement of spin 1/2. Okay, so you have a Stern-Gerlach, a spin 1/2, and you choose an orientation, and you get +1 or -1. Here it's the same thing. I have a photon, I have a polarizer. If the photon goes out in the +1 channel, it's one result. If it goes in the other channel, it's a -1. The polarizer can be oriented, and here the orientation is defined by a unit vector A. Same thing on the other side. So what can I do? I launch a pair of photons, and I look. I find one here and one here, and I make a note. I launch again a pair, and I repeat many times, and after repeating many times, I have probability. So I have this single probability to get +1 here when this polarizer is in orientation A, probability to get -1, probability to get +1 when the other polarizer is in orientation B. You will see this not the most interesting part. The most interesting part is that I can also define joint probability. P++ of AB is a probability to get +1 and +1 when the polarizers are in orientation A and B, etc. This is just a description of an experiment. Now comes Einstein-Rosen situation. Let's suppose that I can prepare the two photons in a state which is described like that. So what does it mean? I only consider degrees of polarization. Okay, I forget about the propagation, it's not relevant for my discussion. So this is only describes the polarization of the photon. X means a photon polarized along this direction, and Y means a photon polarized perpendicular to the screen. So XX is a pair of photons polarized like that. YY is a pair of photons polarized like that. Because of the linearity of quantum mechanics, if this exists and that exists, a priori it is possible to think of a pair of photons which is this plus that. And this is an EPR state. And think for 10 seconds to be sure that you understand that this plus that is not trivial. It's certainly not that. Okay? Why can I say that? Because you see that this state cannot be factorized. If it was that, it would be the product of one photon polarized like that and one photon polarized like that. But here, you can try, you will never be able to factorize that. This is what is called an entangled state. And if you think deeply of it, you will recognize that a state like that is almost as surprising as a Schrödinger cat, which can be both dead and alive. The fact that the pair of photons can be both this and that is really surprising, as you will see. Because as soon as you have a pair of photons with this polarization, it's quite easy to calculate what quantum mechanics predicts for the result of the measurement. So for instance, for this state, quantum mechanics predict that P plus equal P minus equal 1/2, whatever the orientation. It really looks as totally unpolarized light. Same thing on the other side, unpolarized. But if you calculate the probability of joint detection, you find that it depends on the angle. More precisely, 1/2 of the square of the cosine of the angle between the two polarizers. That's the result of the calculation. And let us look at what happens, for instance, when the two polarizers are making measurement along the same direction. The angle is 0. So here you have 1/2. And I claim that this is total correlation. So I'm sure your first reaction is to say, no, 1/2 is not total correlation. Yes, it is total correlation. Remember that the probability to get +1 is 1/2. So if the joint probability is also 1/2, it means that the conditional probability is 100%. So it's totally correlated. If you are not yet convinced, P plus minus, which is proportional to the square of the sinus, it's equal to 0, which means that if you detect +1 here, you will never detect -1 there. Okay? So it's really an interesting situation in which you have a random process here, a random process there, let's say a coin, head and tails, but if you have one result here, you have the same result there. And if you have the opposite, you have the opposite. Okay. Total correlation. So, what do we do with that? Well, first, we are professional, we are scientists, so we are going to define carefully the correlation because we are going to measure it later. So how do I define the correlation between the result here and the result there? Well, it's very simple. The result has nothing quantum. The result is I have a green light and a red light. So the result is a classical random variable. So I just use the usual definition for the correlation of a random variable. What is the usual definition? If I have two random variables, the correlation is the average of the product minus the product of the average, and I normalize. If there is no correlation, it is 0, and the maximum is 1. When I apply this definition, I rapidly find that this correlation is nothing else than the sum of P plus plus P minus minus, and I subtract the crossed result. So probability of identical result minus probability of different result. This is a definition which is classical. Now I insert into this definition the prediction of quantum mechanics. You remember cosine square, sine square, etc. And when I do that, the result is cosine of 2 times the angle. Which means that if the angle is 0, E is 1, as expected. If the angle is 90 degrees, it's -1, which is also total correlation. The fact that it is -1 is very simple. Because I have turned one polarizer by 90 degrees, +1 here corresponds to -1 there, but it is still a total correlation. This is a prediction of quantum mechanics. We are going to use this formula later. Now, some physicists are happy with the calculation and not ask questions, but other physicists, and I belong to this category, are not happy with only a calculation. They want to have an image, kind of interpretation of what happens. And of course, when I have correlations between things at a distance, I don't think that it is black magic, but I think that there is an explanation for that, okay? And so I ask myself, but where does this correlation between distant events come from? And of course, the first idea is to say, let us look in detail into the calculations that we have done. So if I try to derive an image from the calculation, I have a big problem. The problem is the following. The efficient way to do the calculation consists of starting with the state that I've described, projecting it on the result of the measurement, for instance, plus, and square. Good, and I find the result that I have used. The problem with this calculation is that there is no way to make an image in our space. Because this calculation is done in a Hilbert space, which is a tensor product of the space where I describe the first photon by the space where I describe the other one. But the tensor product is an abstract space, and this is not exactly what I would like. I would like to have a description in my space. Why? Well, I like to cite Asher-Perez. Asher-Perez was certainly somebody who liked Copenhagen interpretation and everything. Anyway, in his book on quantum optics, he clearly says quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. And this is my point of view. An image in an Hilbert space may be useful, but I want an image in my laboratory. I have a green light here, a red light. I want to understand that in the ordinary space. And this does not give me that image. There is a way to make an image in our space based on the quantum mechanical calculation. It's a little more involved, but not that much. We are going to assume for a while that this polarizer is closer to the source than the other one. So I have first a measurement here. And I know, I follow the prediction of quantum mechanics, that I have 50% chance to find +1 and 50% chance to have -1. Let's suppose that I have the result +1, which corresponds to the polarization X if I choose this direction for the polarizer. What do I do now? I take my Bible. My personal Bible is Cohen-Tanuji. It's just to tell you that it is really normal quantum physics. Okay, so I take quantum Tanuji, and I find the postulate of projection, which tells me after a measurement, the state of the system is obtained by projecting the initial state onto the eigenstate associated with the result. The projector on that eigenstate is xx plus xy. So when I apply a projector xx plus xy here, what do I get? I get xx. But if I get the result y, the projector is yx plus yy. And if I project, I obtain yy. Good. Now let us continue the reasoning. Now I make a measurement on the second polarizer. If I have obtained this result, it's clear that the result will give +1 if I have a line along x. But if I get this result, it's clear that the measurement of the second photon will give -1. And that's it. I have a nice image in my laboratory of what happens. The first photon is measured, I have a result, and then I do a measurement of the other one, I have the result. And if the polarizers are not the same, I just use a Malus law, and I have the expected result. So it's fine. But is it the end of the story? No, it's not the end of the story. Because this image could not be accepted by Einstein. Why? Because in this image, you are just telling a story, a fairy tale, that when I do a measurement here, the state of the photon which is there changes immediately. This is unacceptable by Einstein. Nothing can be instantaneous for Einstein. And so Einstein was certain to recognize that, and he said it cannot be like that. So what can we do? Well, in fact, correlation is something which happens all the time. For instance, I'll give you an example. You are twin brothers. One lives for Australia, the other one lives for Europe. And when they have the age of 20, you observe they are very far away of each other. They have the same color of eyes, maybe they have the same kind of disease, etc. What do you conclude? Do you conclude that there is an instantaneous connection? No, of course. It's because they were born from the same mother. Okay? And so the idea is that I could interpret this correlation between the photons by introducing the idea that when the two photons are created, they have a common property, and this property will determine the results of the measurement. Okay? Simple. So with this idea, you come to the conclusion that there is something supplementary compared to the description of quantum mechanics. Why? Because look, I may have a model here where I say, oh, some pairs are created like that, and I will find +1, +1. Other pairs are created like that, and I will find -1, -1. So I distinguish at least 2 different kinds of pairs. But in fact, it's clear that I have to distinguish many different kinds of pairs. On the other hand, quantum mechanics describes all the pairs by the same state vector. And Bohr disagreed with the fact that it was possible to do that. And doing that was exactly fulfilling the program of Einstein. This is why Einstein thought that in order to have a reasonable explanation for the correlation, you have to introduce supplementary parameters. Not all the pairs are identical. But Bohr disagreed. Why did he disagree? It's a big question. Because, of course, Bohr wrote a paper which is a reply to Einstein. But I'm sure some of you have read it. And when you read the reply of Bohr, it's not clear at all. And Bohr really makes a lot of arguments, but they are not clear. And it seems that Bohr had the intuition that you cannot complete quantum mechanics. If you would complete quantum mechanics, it would become inconsistent. But anyway, it is an impression that he had this feeling. And in fact, I have read many times this paper by Bohr and other papers by Bohr. And they are all very, very obscure. But one day, I read a statement about complementarity. You know that Bohr was a fan of complementarity. And he was applying complementarity sometime out of its initial field. And in particular, he applied the notion of complementarity to truth and clarity. And he said that clarity and truth are complementary notions. And he made all effort to be as true as possible. And of course, clarity is it's not really a joke. I think that Bohr was extremely careful, and he wanted to not to say more than he wanted to say. And this is why he was not very clear. Anyway, my conclusion is that Bohr disagreed, but he was not able to really contradict the reasoning of Einstein paradoxically. Okay. What happened? Nothing. Bohr and Einstein discussed for the rest of their life. Einstein died in 55. Bohr died in 60-something, 62, I think. And it's clear that they discussed until the end. And even Bohr was still arguing after the death of Einstein. So he was obsessed. So it was not a small problem. But everybody else did not care. And there is a good reason. Quantum mechanics was accumulating success. So the young physicists, they use quantum mechanics, it works, they find wonderful results. Why would they care about a discussion about old people? Okay, all growing. In my opinion, there is another good reason why even the people who thought about that did not care too much. When they looked a little bit in detail in the discussion between Einstein and Bohr, they found that there was no disagreement on the validity of the quantum formalism. Einstein did not say that quantum mechanics is wrong. He said that he insists on giving another interpretation. So you are a working physicist. You are using quantum mechanics. It works. Bohr and Einstein agree that the mathematical formalism that you are using is good. Why would you care? You say, okay, when I retire, I will think about this thing. But now, I think it was the real reason why almost nobody cared. But then, somebody arrived on the stage, John Bell. And in 1964, John Bell said, let us take seriously the idea that in order to understand the correlation, we introduce new parameters. So we have this parameter, lambda, which is associated to a given pair. So when the two photons are emitted, there are something in common, which is this lambda. Then this lambda will determine the outcome of the measurement here and the outcome of the measurement there. So I need to introduce a function, capital A of lambda and A, with two possible values, plus 1 or minus 1. This function will tell me, when a photon has a property lambda, this function will tell me if I find plus 1 or minus 1. Same thing on the other side, okay? And now, of course, I have many different lambda, so I must describe the distribution of this lambda by a density of probability, which is a honest density of probability, that is to say positive and normalized, okay? And if I have a model with a specific form for capital A, capital B, and rho, then I can calculate the correlation coefficient. It's nothing else than the average product AB. You can check that, it's almost trivial, okay? Good. So let us give an example. Let us assume that the two photons are emitted with the same polarization. So lambda is the direction of the polarization, it's the common polarization. They arrive on the polarizer, and I have to invent a function capital A. What should I do? If the polarizer is parallel to lambda, I want to have plus 1. If it is perpendicular, I want to have minus 1. And I want it dichotomic, so I have to put a frontier somewhere. And obviously, I put the frontier at 45 degrees. Okay? This function does the job. It's the sine of the cosine, the sine in the same plus or minus, of the cosine of twice the angle between the polarization and the polarizer. Okay? So I have capital A, capital B. Now what should I take as rho of lambda? Well, I know that the result at the end of the day is rotationally invariant. So I take rho of lambda rotationally invariant, so 1 over 2 pi. Good. If I use this very simple model, the result that I find for the correlation as a function of the angle between the polarizer is the red lines which are here. It's not so bad. The quantum prediction is in blue here, and with this extremely simple model, I find the red line, which means that I find the total correlation at 0 degree, I find the total correlation at 90 degrees, I find that the correlation is 0 at 45 degrees, and in between it's not exactly, but it's not so bad. Okay? So once you find that, you say, okay, I'm a naive guy, but I have a friend who is a good theorist. He knows everything about special function, Hankel function, Bessel function, so probably he will be able to design a model which will have the prediction of this model exactly identical to quantum mechanics everywhere. So you visit your friend and you say, look, I have this problem. Don't you think that there is a better model agreeing with quantum mechanics prediction at all orientation? And either your friend does not know or Bell theorem, and then he looks into Abramowitz and all this Mathematica or whatever, you know, or he knows Bell theorem and he immediately replies no. Because Bell's theorem tells you no. Bell theorem tells you that there is no local hidden variable theory, I will explain the words, in the spirit of Einstein idea, which can reproduce quantum mechanical prediction at all orientations. And let us look again at our example. It can reproduce here, 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 but not here, okay? And so, impossible to cancel the difference everywhere. How does it work? Bell's inequalities. So this is a useful form of Bell's inequality when you do experiments. So this is the one I show. If you admit that each of these correlations, here, function, is obtained with capital A, capital B, and rho. I don't take a specific form. I assume that capital A, capital B, and rho do exist. And the only thing that I demand is that capital A is dichotomic, plus 1, minus 1, capital B is dichotomic, and rho is a good density of probability. Then you can demonstrate that if you consider two orientations on one side, A and A prime, two orientations on the other side, B and B prime, you have four correlations, AB, AB prime, A prime, B prime, and Bell can demonstrate that this quantity cannot be bigger than 2, it cannot be less than minus 2. So you may ask me, where does it come from? If you ask me the question at the end, I can do the demonstration in 2 minutes on the blackboard, okay? It's high school mathematics. Well, at least high school when I was in high school. Really, it's high school algebra to demonstrate that, okay? So, you may ask me, but there is no mistake with this minus sign? No. Why a minus sign? Well, because Bell was a genius. He found that if you have a minus sign, it's especially interesting. And I show you that it is interesting. Because now, let us consider the prediction of quantum mechanics for a set of orientation which is shown here. So AB is pi over 8, BA prime pi over 8, and A prime B prime pi over 8. So 2 times pi over 8 is pi over 4. Everybody follows. Almost everybody will follow if I say that cosine of pi over 4 is, Ivan? 1 over root 2. Thank you, Ivan. So now I have 1 over root 2, 1 over root 2, 1 over root 2. Now let us look at A, B prime. I double the angle, and now it's more complicated. The cosine is negative. It's minus 1 over root 2. But there is a minus sign here. So it's another 1 over root 2. And the result is that for this set of angles, quantum mechanics predicts 2 root 2, which is obviously bigger than 2. So what is the conclusion? The conclusion is that if you do this set of measurements, the result that you will find, if quantum mechanics is right, cannot be described by a model with capital A, capital B, and rho. And it's not one specific model, it's all the possible models. All hidden variable theory following that model are excluded. That's the result. And now you see that the conflict, the possibility to complete quantum mechanics according to Einstein ideas, is no longer a matter of taste or of interpretation. It has turned into an experimental question. Let us do the experiment. Do we find more than 2 or less than 2? Okay. Before applying for a grant to do the experiment, let us look a little bit at the hypothesis necessary to obtain Bell's inequality, because at the end of the day, it may be that there is something wrong with the demonstration. There are dozens of papers looking at that, and the first point is that there is no mathematical mistake. Again, high school algebra, no mathematical mistake. Then you may question the hypothesis. What are the hypotheses necessary to have this model? Well, you must admit that there is a supplementary parameter, lambda, called hidden variable, which is carried by each particle, and this lambda will determine the result of the measurement here. This hypothesis that the particle brings with it parameter which determines the result of the measurement is called a local realist point of view. Why realist? Because having lambda is what Einstein called the physical reality of the system. Local because it belongs to the environment of the system, is not spread in whole space, okay, and it determines the result. So it is a local realist worldview. Now in this fantastic paper, fantastic because it is simple. In this fantastic paper, John Bell insists that there is another hypothesis. The other hypothesis is what is called Bell's locality condition, which is the fact that the result on one side is not allowed to depend on the orientation of the other polarizer, and vice versa. And similarly, in the same spirit, the way in which the pair are emitted here, that is to say the distribution rho of lambda, is not allowed to depend on the orientation of A and B. If you would allow that, you could not demonstrate Bell's inequality. So in other words, you need to have this condition if you want to be able to demonstrate Bell's inequality. And Bell goes on in his paper and says, of course, the hypothesis is very reasonable. We don't think that the result here can depend on the orientation of the other side. But after all, it's a fundamental question. There could be an unknown interaction which says that this is not true. And then Bell proposed, it said, if we could do an experiment with variable polarizers, of which the orientation are modified faster than while the photons are flying, then what you have here could not depend on the orientation on the other side because it has changed at the last moment. And relativity forbids that anything goes faster than light. And of course, similarly, if you change the orientation of the polarizer while the photons are in flight, the way in which the pair are emitted here cannot depend on the orientation which will be chosen later, right? So we have really, in an experiment like that, a conflict between quantum mechanics and Einstein's worldview. We have introduced the point of view of Einstein 2 times. One, to say that we use the hypothesis of local realism, and the second, in order to say that we separate the two ends of the experiment based on relativistic causality. Okay, it's time to think of doing experiments. Or maybe to look into the experiment which have been done. Do we have results able to test Bell's inequality? Surprisingly, when Bell's theorem came out in 64, 65, there did not exist any available result able to test Bell's inequality. This shows that Bell's inequality are very general. Not only they apply to any experiment that they could describe with classical theory, classical mechanics, or classical electrodynamics, but even in experiments where people are convinced that you absolutely need quantum mechanics to describe it, anyway, in this experiment, you don't expect correlation as strong as correlation which violate the Bell's inequality. And so it was necessary to invent new situations where the test is possible, where there is a conflict, and it was the immense merit of the paper by Clauser, Horn, Chimony, and Holt. It was a proposal in 1969, which was a practical proposal to a situation where you can have the conflict. And from this proposal, there have been many, many experimental tests. So I like to say that there are 3 categories. There were the heroic pioneers, Clauser and Friedman in 1972 in Berkeley. They did a test. They found a violation of quantum mechanics, a violation of Bell's inequality, and an agreement with quantum mechanics. But at the same time, in Harvard, Pitke was considered a very serious physicist, found a result in agreement with Bell's inequality and in disagreement with quantum mechanics. 4 years later, in '76, in Texas A&M, Ed Fry did an experiment where he had a clear trend in favor of quantum mechanics. The experiment of Fry was more convincing and more accurate than the previous one because he was the first to introduce a laser to produce a pairs of entangled photons, and the signal-to-noise ratio was better. To make a long story short, in the experiment of Clauser and company, he had to accumulate for days because the statistics was very poor. For Fry, it was hours. The problem with this experiment is not only that the signal-to-noise ratio was not fantastic. The main problem is that for many technical reasons, the scheme of these experiments were not exactly the schemes that I have presented. And this is why in 74, 75, I decided to embark in a new series of experiments, and the goal was to realize experiments with schemes as close as possible to the scheme discussed by the theorists. Because when you speak of fundamental things, you don't want to have plenty of intermediate steps. You want to test directly the theory. So I did this series of experiments, and I will a little bit describe them. And then in '82 the result came, I will show you. And then at the end of the decade, by the end of the decade, people began to develop sources of entangled photons, yet better than mine. Mine was much better than the previous one, but then they developed sources of pairs of entangled photons much better than mine, and with this they did fantastic tests, and I will give you an idea of all these fantastic tests. Okay, I described in a few words the source of entangled photon that I do. The idea is the following. These have been recognized by Clauser. If you can excite an atom to a level J equals 0, which is not degenerate, and you let the atom decay by spontaneous emission, having a first photon emitted towards a level J equal 1, which has a Zeeman sublevel m equal 1, m equal 0, m equal minus 1, and then decay to final state, which again is not degenerate. In fact, if you look at what happens, if you observe the two photons in opposite direction, you can ignore the intermediate level m equals 0, but you see that this decay can proceed through two possible paths. One pass here and one pass there. This path gives a pair of circular polarization, sigma plus, sigma minus, and the other path gives sigma minus, sigma plus. And if you re-express the circular polarization as a function of linear polarization x and y, you find exactly the state that you want. So this is a way to produce the EPR-like state. Okay. Now the difficulty was to excite the atom here. In the experiment of Friedman and Clauser, they were exciting that state by ultraviolet absorption. But ultraviolet absorption cannot go directly here because the two levels have the same parity, and absorption is done by an electric dipole transition, which is an odd operator. Okay? So in fact, they were exciting levels somewhere here, and sometimes it would decay here, and they were happy, but most of the time it would decay through other states, and you would have the second photon, but not the first photon of the day. Okay? So this is why the signal to noise ratio was not good and the yield was poor. When I embarked into that in 1974, there was a new technique which has just been developed. It's called two-photon absorption. It is a nonlinear effect. If you add the energy of two photons, and if you are exactly resonant here, then you can excite this level. And now you have the product of two odd operators. It is an even, the product is even, and you can be very efficient in doing that. And once you have done it, the atom is here. What can the atom do? Only deliver the pair of photons that you expect. So with this source, the yield was fantastic. Just to give you an idea, I add everything, all the losses being taken into account. At the end, I could observe 100 coincidences per second. Coincidence means joint detection of this and that. And this is fantastic, because in this kind of experiment, there is absolutely no noise, no background, because correlation eliminates all kinds of background that you have. Which means that in 100 seconds, that is less than 2 minutes, you count 10 to the 4th events, which means a statistical accuracy of 1%. Okay, the statistical fluctuation is good. So in only 2 minutes, you have a statistical accuracy of 1%. This makes any experimentalist very happy. So what we did, the first experiment we did was similar to the one done by previous researchers, and one of the big differences between these experiments and the ideal experiment is that nobody at that time was using a polarizer where you had two output channels. There was only one output channel. One polarization is transmitted and the other one is blocked, just like in a Polaroid. Well, this was a sophisticated version of the Polaroid. It was a polarizer with pile of plates. 10 plates at Brewster angle. Technology of the 19th century. Very good. At that time, it was the best polarizer you could get for this kind of piece. Okay? But it was not perfect, but at least we repeated the experiment of the predecessors, and we found violation of Bell's inequalities, but we did something in addition. We took the polarizer at 6 meters on the source on one side, 6 meters on the other side. Why? Because sometimes in the discussion about entanglement, some physicists will tell you, look, entanglement does exist. We know it. If we would not accept the idea of entanglement, we could not render an account of the spectrum of helium. You know that in helium you have 2 electrons, and some states of the helium are entangled states. So you could not describe the spectrum of helium if there was no entanglement. But entanglement is a property of the microscopic world. When you are going to go at macroscopic distance, entanglement will disappear. And so you would ask to this theorist, but what is the scale at which it disappears? And the guy scratches his head, and there is only one scale here. It's the length of coherence of the photon. So we tell you length of coherence of the photon. And here you have a lifetime of 5 nanoseconds. And the length of coherence associated to 5 nanoseconds is 1.5 meters. So by going at 6 meters, I was definitely going beyond the length of coherence of the photon. Entanglement was still there. Bell's inequality was still violated. Okay. After this first warm-up, I could obtain polarization splitter of that kind. So young people will tell me, well, it's simple. You go on internet, you order it, and next morning you have it by that time it did not exist. And you know what I had to do to get a polarization splitter like that? Well, there was a laboratory of research, Philips Research Lab in Eindhoven. They were developing stuff like that. And I could bribe of one of my friends with a few bottles of French wine. And they built for me such polarization beam splitter at my wavelength, at the wavelength which I needed. This was a problem. They started developing it for standard wavelengths of laser, but not for my wavelengths. And just to give you an idea of the difficulty, you have to realize here 34 layers of dielectric, which with well-defined index of refraction and with precisely determined thickness. So it was a really achievement. It was worth an excellent French wine. But what is the benefit of that? The benefit is that in a single run, you choose a set of orientation, A, B, and in a single run, 100 seconds, you get 4 numbers, n plus plus, n plus minus, minus plus, and minus minus. And once you have that, you have your correlation. Because the correlation, well, this is the two-channel polarizer. The correlation coefficient, once you have the 4 numbers, is nothing else than n plus plus, plus n minus minus, minus this one, and you normalize by the sum of the 4 numbers. It's a self-calibrating experiment. And this is absolutely remarkable. Because if you don't have a self-calibrated experiment, you have the problem, is my source exactly stable? Don't I have fluctuation? Moreover, if you look into the details of the reasoning for demonstrating Bell's inequality, it's annoying to have supplementary calibration. So with this, it's very good from a conceptual point of view and from an experimental point of view. And the result is here. The famous quantity S as a function of the angle between the polarizer. These are the points. And we are going to spend 1 minute on that curve. That curve is very interesting. The green curve is a prediction of quantum mechanics, which had been calculated before doing the experiment. You see that it does not start exactly from 2, etc. Why? Because the experiment is not totally ideal. The polarizers do not transmit 100% of the good polarization. They transmit only 98 or 99%. They don't totally block the orthogonal one. They pass 1%. So you measure that, you include it. Moreover, the simple reasoning that I have shown is based on the fact that the 2 photons are emitted along the same direction. But in fact, you have solid angles to capture the photon. So it's a complicated calculation, Bessel function, etc., etc. But at the end, you calculate the fact that because of the solid angle, you predict not exactly 1 as a correlation function, but a little less. So the green curve takes into account all the inefficiency which has been measured before. And then you have the results here, which are the result with plus or minus 2 standard deviation. Look, when I saw that, I say, yes. I can tell you, I was not expecting a result like that. Okay. And when you look at the result, if you look what happens here, or what happens here, you get a violation of Bell's inequality by more than 40 standard deviation. I cannot even calculate what p-value it is, probably 10 to the minus 30 or 40 or something like that. But this curve also shows something interesting. If you don't know Bell's inequality, but you know that you have entangled pairs of entangled photons, you say, oh, I want to test it. And you cannot afford to do too many experiments because the signal is poor. What are you going to do? You are going to do 0 degree, 45 degrees, and 90 degrees. And at 0 degree, at 45 degrees, and at 90 degrees, you don't predict any conflict between quantum mechanics and hidden variable. And in fact, this has been done. In the 50s, some people have done measurement of that kind with photon gamma produced in the disintegration of positronium. And they could not afford to do a long experiment because it was an expensive experiment. They have only a limited amount of time in their experiment. So at that time, they did not know Bell's inequality. They had done 0 degree, 45, or the equivalent 45, and 90. Okay? And so when Bell theorem was discovered, they looked into this data, and there was no possibility to do this. So it tells you that Bell's theorem is really a guide to do this kind of test. Okay, let us continue. You remember that Bell had told us that the real ultimate test would be a test in which you change the orientation of the polarizer while the photons are in flight. So let us look again at the polarizer, the two-channel polarizer. Well, sorry for the photo, but it's extracted from my thesis 30 years ago. Here you have one photon. The photon arrives here. You have the polarization splitter here, transmitted channel, a very heavy photomultiplier, reflected channel, very heavy photomultiplier. Why heavy? Because you have several shields. A shield of copper to get shielded from radio frequency. A shield of lead, because you may have cosmic ray arriving on the ceiling of the building and a shower, and you want to get rid of this possible coincidence due to cosmic ray, etc. The result is that this has a weight of 50 kilograms. Now the distance between here and there is 6 meters. Light takes 20 nanoseconds. You are not going to turn 50 kilograms to 20 nanoseconds. So this is what I have proposed to do and what I did. Rather than trying to turn the photomultiplier, use a switch here which is able either to let light go like that or send the light towards this direction, and then you put a second polarizer in orientation A prime. And now you have this switch which is switching every 10 nanoseconds, which means that every 10 nanoseconds you either analyze along direction A or along direction A prime. Of course, you do the same thing on the other side, and now you have the experiment with the orientation change while the photon are in flight. This experiment was certainly not ideal. First, these switches were reducing the size of the beam here, so that the signal was weaker, and rather than taking 1 minute, it would take like 15 minutes to have a decent result. Well, 15 minutes is not too bad. You can afford to do it. It's better than 15 days, I can tell you. 15 minutes is okay. But the main drawback or inefficiency, or call it imperfection of this experiment, is the fact that the switching were not really random. It was periodic generators, okay? So you can argue that it is not random. Well, anyway, we are not totally stupid, so what we did is having a generator here and a generator there, which are at different frequencies, and moreover, they were not very good generators. They were drifting. On purpose. They were drifting differently here and there. So, okay, both ends were not correlated. Anyway, the ideal experiment would demand a random number generation. We could not afford to do that. whoops. But the result was a convincing result. Accumulated for a few hours, we obtained a violation of Bell's inequality by 6 standard deviation, and for the first time, each measurement was space-like separated from the setting of the distant polarizer. Einstein's causality was enforced. Okay. As I told you, let's say 1 decade later, people began to develop sources of pairs of entangled photons based on nonlinear crystals in which an ultraviolet photon is split into 2 red photons, okay? And if you do it well, if you take the correct crystal, you cut it well, then you can be in a situation where your 2 photons, entangled photons, are produced in well-defined direction. And once you have produced your photon in well-defined position, it's remarkable because then you can fit them into an optical fiber. For me, I had lenses that big, okay, etc. No question of putting it in an optical fiber. But with this source, you can fit the photon into an optical fiber, and then you can go far away. So these are 2 experiments which were done in 98, 97 or 98. Nicolas Gisin in Geneva, he was able to use the commercial optical fiber network of Swiss Telecom. And at night, he could do his experiment. At night, you know, Swiss people are quiet. At night, they sleep. And meanwhile, Nicolas Gisin was doing his experiment. And he found a violation of Bell's inequality at 30 kilometers distance in these optical fibers. At the same time, Anton Zeilinger and Greg Weiss in Innsbruck did an experiment which is absolutely wonderful. It was the experiment I was dreaming of. Okay? Why wonderful? Because they produce a pair of photons here, they insert 1 photon in optical fiber and the other one in the optical fiber, and the time to travel is long enough that during the time of propagation, they can operate a random number generator which decides on the orientation of the polarizer. And more than that, and you will be at the end why it's so nice, and I was really dreaming of that skill. Well, actually, Greg Weiss, who wanted to do this experiment, asked me what I would do, and I told him, this is the experiment that you have to do. It was a dream, but he made the dream a reality. Now, here, you have the result, and you register the result, and you have an atomic clock, so you register everything. You see, at this time, this was the orientation of the polarizer, and I got +1. Same thing on the other side. And when everything is finished, you take the 2 sets of data, you put them in front of each other, and then you determine the correlation coefficient. And they found agreement with quantum mechanics and violation of Bell's inequality. Good. Now, there have been more and more experiments, and you may have heard of loopholes. What is a loophole? A loophole is the fact that when the experiments are not perfect, then if you are an advocate, a strong advocate of hidden variable, you can say, oh, but I can't exploit the weakness of your experiment to have a hidden variable model which anyway reproduces a prediction of quantum mechanics. First example, locality loophole. If you do experiment with static polarizer, then you can have a model in which what happens here depends on the orientation of the other side, and that's it. So closure of the locality loophole demanded to have polarizer switch during the propagation. The experiment that I did in 82 was the first one, and in 98, in Innsbruck, Zeilinger and Weiss did these experiments. So locality loophole was closed. Now there was another loophole, the so-called sensitivity loophole. The sensitivity loophole is linked to the fact that we were operating with photomultiplier with a quantum efficiency of, let's say, 20 or 30%, okay? Which means that you detect only 30% of the photon. You lose 70% of the photon. And then, if you have an advocate of hidden variable theory, you say, in fact, the sample of pairs of photons that you observe is not a faithful representation of the whole distribution. And there is a conspiracy which makes the selection different in this orientation and that orientation. And if you accept this reasoning, you find that you have to go to quantum efficiency larger than 72 or 75% in order to avoid this loophole. So this was done year after year. First there was Dave Wineland in Boulder. He did an experiment with trapped ion. Then with photons there was a series of experiments, and this experiment closed the sensitivity loophole. Now still the paranoiac defender of hidden variable theory say, oh, but you close one loophole, you close the other one, but how do you know what would happen if you would close the two? So in 2015, then there were 3 experiments which were published in which the people closed simultaneously the 2 loopholes, the locality loophole and the sensitivity loophole. One experiment was in Boulder, in NIST, one is in Vienna, still Zeilinger, now is in Vienna, and one experiment was in Delft. And these experiments are more or less convincing. They are okay. If you want to know exactly what I think of this experiment, you can read this. It's a viewpoint. You know what is viewpoint? Viewpoint is a news and views of American Physical Society. So I did not write the news and views for Nature. I write it for APS because of several reasons. Yes. So this is free. You can download it from the web and you can read as how I explain all that. Okay. Conclusion. Einstein's worldview, Einstein's local realism is untenable. What can we conclude? Well, in fact, Einstein told us. So you may be surprised. Einstein did not believe in what he was saying. Yes, he was believing. He was believing it. But he said, if I was not right, this is what you would have to accept. So what did he say? He says that if he was not right, you would have either to drop the need of the independence of the physical realities present in different parts of space, or accept that the measurement on one side changes instantaneously, this is the word of Einstein, the real situation on the other side. This is called quantum non-locality. We have to accept something of that kind of quantum non-locality. Some people do not like the idea of non-locality, and they prefer to invoke something which, in my opinion, is similar, but it's phrased differently. It's quantum holism. And you will see that quantum holism is very interesting for quantum information. The idea of quantum holism is to say that even when my particles are well separated, the state of the system, or you have more in the description of the whole system than in the reunion of the property of the first and the property of the second. There is more in the whole than in the sum of the combination of the property of the first and the second. So it's a whole, quantum holism. You will see why it is interesting. Now, a warning. Even if you accept the idea of quantum non-locality, and I do accept the idea of non-locality, you cannot use this non-locality for transmit faster than light an utilizable signal. And I encourage you to ask me a question about that, because I think that understanding that is really illuminating. But I prefer to go on this one. So now, we know that the Bell's inequality are violated, and this has prompted the emergence of the new quantum revolution. The understanding of these extraordinary properties of entanglement has triggered this research field. And I have cited some names. It has triggered the emergence of ideas about quantum computing. And first there was a paper of Feynman in 1982 when he recognized that entanglement is more than wave particle duality. David Deutsch. Quantum lithography has been invented by Bennett and Brassa in 1984 and Eckert in 1991. The difference is the following. Bennett and Brassa published their idea in an obscure proceedings of the conference about computing, while Eckert published it in Physical Review Letters and cited Bennett and Brassa. But we must give credit to Bennett and Brassa. Quantum teleportation, you have heard of it, quantum simulation. And entanglement is at the root of most of these schemes. So we just described one scheme. The scheme of Arthur Eckert for quantum cryptography, I think it's quite interesting. What is the problem? Alice and Bob want to exchange information, and without the awful eavesdropper, eavesdropper with a mustache, it's a bad guy. So the eavesdroppers try to intercept the information. What can they do? Well, since Shannon, we know that there is a solution which is absolutely safe. It's called one-time path. The idea is the following. Alice and Bob have a random series of 1 and 0 which are strictly identical. Alice will encode with this, and Bob will decode with that. And it's demonstrated absolutely safe under one condition. The message should not be longer than the key. Because if the message is longer than the key, as you know, in any language, there are repetition, and it's a way the expert can decipher as soon as there are repetition. So now you have the problem of distribution of the key, because Alice and Bob have used their key, and now they want to send another message. So you must be able to distribute the key. And the Eckert solution to distribute the K is quantum K distribution using pairs of entangled photons. You remember, if the polarizer are along the same direction, if you have +1 here, you have +1 here. If you have -1 here, you have -1 here. And it is totally random as far as we understand it. So, in a sense, if you have followed what I was saying, because there is no hidden variable, the polarization and the result +1 or -1 is not yet decided when it passes in front of the eavesdropper. The +1 or -1 will be decided at the last moment, so there is nothing to spy. Let us suppose anyway that the guy is so smart and he has a fantastic technology that he is able to do the following measurement. He puts a polarizer along a certain direction, measure the result, and then send a photon to Bob with exactly the same polarization that the one he has found. What will happen? By doing that, he has, in a sense, collapsed the wave function, and in a sense, you have now a hidden variable. So, Alice and Bob can detect the fact that there is a guy doing that by testing Bell's inequalities. Because if there is a hidden variable, Bell's inequalities are not going to be violated. So the idea is that Alice and Bob have a choice between some various orientation, 22.5 degrees, etc., and 0 degree, okay? And each of them make a random choice. Okay? When everything is finished, they use an open radio, everybody can listen, and one of them, let's say Alice, announces, okay, in first measurement, my orientation was this one, and I found +1. In the second measurement, my orientation was that one, and I found -1, etc. And they go on like that. And then Bob can find the situation when it was 22.5 degrees or 67 degrees, and he can test Bell's inequality. If there is violation of Bell's inequality, he is sure that there is nobody on the line. And then he can decide to look for the situation where the polarizer were in the same direction, and now we say, okay, our key will be built with measurement number 1, 7, etc. So this is called security, what is the term? It's a Security and what? Unconditional. Thank you. Unconditional security. Okay. So you see that this is an example of a quantum technology. Okay. You know that recently the Chinese team has been able to distribute a K like that from a satellite by sending entangled photon from a satellite. So it becomes a serious technology. Now, second example, and then I will stop. Second example is the idea of quantum computer. The idea of quantum computer is massive parallelism. And I explain why. That's the idea that I have raised, that in an entangled system, there is much more than in the addition of the various parts. So I show it. If I have two entangled qubits, I have a space, a Hilbert space of dimension 4, because the basis is plus 1, plus 1, plus minus 1, minus 1, plus 1, and minus 1, minus 1. Dimension 4. 3 entangled qubits, dimension 8. 10 entangled qubits, dimension 1000. 20 entangled qubits, dimension 1 million. So let us stop at this point. How much did I say? 20 entangled qubits. If I can do an operation, which is a unitary operation, which transforms my state, which is in this Hilbert space, I change simultaneously 1 million components. So I have massive parallelism. That's the idea underlying all these ideas of quantum computer, quantum register, etc. I don't say that it is working. I say that it is the idea, and we have a few examples, for instance, the short algorithm for factorizing number, where this property can be exploited to have an exponential acceleration of calculation compared to a classical machine. And now at this point, I would like to tell you what I call the second quantum revolution. The second quantum revolution is based on two notions, on two concepts. First, entanglement. If you have not yet understood that I think that entanglement is something new, probably you were sleeping. But there is something else that I have not emphasized and which must be emphasized as much as entanglement, is the fact that in the last decades, let's say starting in 1970s, physicists have learned to observe, control, manipulate single quantum objects. Before that time, they only thought about large ensemble. You have a large ensemble of atoms, you shine light, you observe fluorescence light. You use density matrix. And so, when you have large ensemble, you have no problem in having probabilistic prediction. But when you have a single quantum object, the question of probabilistic prediction becomes more subtle. So in fact, being able to trap a single ion, a single electron, to manipulate single atoms, to produce single photons, to observe quantum jumps, this, in my opinion, is as important as entanglement, and the second quantum revolution is based on these two properties that we can implement technically. So, to conclude rapidly, you know that the first quantum revolution was based on wave-particle duality. It has changed the society because it has given us laser, integrated circuit, and led to the information and communication society. So it was first conceptual with particle duality, and then it has become technological. And now we're in the stage where we understand the new conceptual revolution, entanglement plus individual quantum systems. Will we have a new technological revolution? Well, there are people who think seriously about it. European Commission has put €1 billion on the table. It's not bad, you know, euro is slightly more than $1, so €1 billion is not bad. And you have companies like Microsoft, Google, IBM, Atos in France. They invest on quantum information. I don't know if it will work. The most likely roadmap is probably from proof of principle with objects which are given to us by Mother Nature, photons, atoms, ions, molecules. But now you have people with technology of microelectronics, okay? They are able to build solid-state devices which are quantum, okay? And so, all this is a fascinating issue. We don't know the issue, and this is why young people who decide to work in that are right. And to finish, I just want to say that when I was completing my experiment in 1982, it was my PhD thesis, but on the last year of my experiment, I had 2 young master students. You should know them. Maybe you don't recognize, well, Ivan has recognized. This one is Jean d'Albert, and this one is Philippe Rangier. They were master students, and they came to complete the experiments with me. And I also a fantastic engineer. And just before you applaud, if you like, or not, if you don't applaud, I just want to say that now, in the Institute of the Graduate School, we have laboratory classes 5 days a week. Students violate basic politics. Thank you very much.
I just want to add one anecdote before we start questions, or I meant to say.
I'm afraid that would be...
Yeah, well, no, this is an amazing thing. So, not only is Alain being incredible business, but he's a very gracious human being. And when I was a beginning professor, he invited me to his home where he made me an amazing dinner and shared one of those amazing bottles of wine, and I didn't even give him a polarizer. So. True story. All right, yes.
There's a question we were supposed to ask.
You want that one? Oh,
Yes.
Yeah.
good. Thank you. Excellent question. No faster than light signaling with... You remember, according to what I explained, when Alice changes the orientation of the polarizer here, something changes instantaneously on the other side. The state of the other photon changes instantaneously. But the question is, can Bob know that the state of the photon has changed? If Bob is only looking at what comes here, you remember, it's just random, +1, -1 randomly. So Bob cannot know that something has changed. In order to know that something has changed, he must be able to look at the correlation. And to look at the correlation, there must be a cable which goes from here, which comes there, and then by comparing the result here and the result there, by comparing this result, he can look at the correlation coefficient, and now he knows that Alice has turned the polarizer. But of course, this channel is a classical channel, does not go faster than light. Okay? At this point, I see the faces of people, they are disappointed. They say, oh, we have lost our time, it's not interesting. Hold on. Let us suppose that Alice and Bob do their experiment as Weiss and Zeilinger did it. That is to say, here they do their business, they register everything with an atomic clock. He does his business, he registers everything with an atomic clock. When everything is finished, they look at the result. And they have to recognize, they have to acknowledge that something did change instantaneously. They could not use it on the spot, but if you look at it from the point of view of an historian, of an archaeologist, you have to recognize that something did change instantaneously. Bizarre, isn't it? And so, you know, when you do this kind of reasoning, you cannot help scratching your head and asking the question, is it a real problem? And I could tell you my answer, but I prefer to tell you the answer of a famous physicist. You remember, Carl? This physicist wrote, it has not yet become obvious to me that there is no real problem. I cannot define the real problem, therefore I suspect there is no real problem, but I am not sure there is no real problem, and so that's why I like to investigate things. And that physicist is Richard Feynman in the paper which is considered the founding paper of quantum information. And the reason why I tell Carl, because in '84, Carl had invited me in Caltech. I gave this talk in front of Feynman, and at the end, I projected that. And then I received a letter of Feynman saying, I must admit that the quotation of mine was right in the context. Okay, so make your choice, make your own conclusion. Is it a real problem or not? You can follow the conclusion of Feynman.
What does instantaneous mean?
This is a very good question. It means that, well, if you consider the world in which we live, you have masses everywhere, and there is a preferred frame of reference. So you can think that there is something instantaneous in a preferred frame of reference. Okay? And in fact, John Bell was trying, he failed, but he was trying to find a microscopic theory which would not be relativistically invariant, but when you would average, then it would become relativistically invariant. But at the level of the microscopic event, why not having something which is faster, which is instantaneous and faster than light? But I agree that it is shocking when we have learned relativity and Lorentz invariance and things like that. But we could declare that for this kind of phenomena, there is a preferred frame of reference.
So
Yeah,
naively,
one question.
naively, I mean, I think you hinted that it may be a real problem when you talked about the archaeologist. So can you go and give your opinion if it's a real problem?
Well, yes, I'm going to make several comments. First, like Feynman, people who have recognized that the situation is weird, surprising, shocking, problematic, many of these people have discovered something interesting for quantum information. So at least it's interesting to recognize that there is a equation, and Feynman, in the same paper where he writes that, invents the basic notion of quantum computing. Okay? So this is the first comment. Second comment, my personal vision. As I told you, I am somebody who likes images. My image is an image in which I have instantaneous collapse of the wave function, etc. I know that there is no contradiction between that and the fact that you cannot transmit information faster than light. Moreover, so let's suppose I say, oh, if I put a polarizer here, I do that, and then I have an atom and I have this, that, I accept that there is instantaneous interaction, and I say, oh, the situation is very interesting. You know what I will do? I will do the calculation with standard quantum mechanics and check if that calculation agrees with my intuition. Okay? So at least I can tell you, it's my experience, that accepting this kind of crazy images gives me an intuition which is fruitful. I don't say that the world works like that. I don't know if the world works like that or not. But accepting the idea that there is instantaneous connection in the world allows me to have interesting intuitions. I cannot tell you more. But it's not so bad.
No, it's just time for our last question.
I don't think I understood this thrust of one of your slides. Were you saying that quantum non-locality and quantum holism were the same concept or different concepts?
Same.
Same, okay.
Same, because, look, I have a system here, and I have a system there. If they are in instantaneous connection, it means that it is a whole. So, in my opinion, the same.
Okay.
Well, this has been incredibly interesting, fruitful, and exciting for all of us, and we're delighted. Thank you very much.